So, let's go. You're standing on the moon. You've trained for this your whole life. Hundreds of simulations, thousands of hours, every scenario you could imagine. And standing here, right now, nothing looks right. The shadows are wrong. The sun hasn't moved in hours. And Earth is just hanging there on the horizon, staring at you. Not moving. Not setting. Just watching. You were told this was humanity's triumphant return. Nobody mentioned it would feel like this. Here are 10 terrifying things the next moon landing crew will face that Apollo never did. Number 1, the elevator. When the Apollo astronauts wanted to get off their lander, they opened a hatch, climbed down 9 rungs of a ladder, and stepped onto the moon. The whole vehicle was about 7 meters tall. Simple. Almost insultingly simple. The next crew doesn't get simple. Starship, the vehicle carrying humans to the lunar surface this time, stands 50 meters tall. That's a 10-story building planted on the moon. The crew cabin sits about 35 meters up, and the only way down is a single external elevator that rides along the outside of the vehicle. You step in, it lowers you past 10 stories of spacecraft, and you step off onto the moon. One elevator, no ladder, no backup. NASA's own Inspector General looked at this setup and used the phrase, critical single point of failure. In plain English, if the elevator jams while you're on the surface, there is currently no other way back into the spacecraft. No rope, no alternate hatch, no confirmed plan B. The program is working on mitigations, but none have been publicly announced, and the terrain makes it worse. The South Pole isn't flat. Parts of the landing zone slope up to 20 degrees. You've got a 50-meter rocket balanced on a hillside with its center of gravity extremely high, and the only thing connecting the crew to the inside of it is one elevator mechanism that has never been used on the moon before. Engineers have flagged tip over as a real concern. Not a fringe worry, a formal one. Apollo had 9 rungs, and gravity, that was enough. Nobody thought to make it more complicated because more complicated is how people die. Number 2, shadows that lie. On Earth, you trust shadows. They tell you where a step drops, where a ledge is, where the ground changes. Your brain has been reading them since before you could walk. That skill, that automatic unconscious depth perception, is about to become completely useless. At the South Pole, the sun never actually rises. It skims along the horizon, sliding sideways, never climbing more than a few degrees above the ground. And when sunlight hits at that angle, shadows don't point away from things, they stretch away from them. A rock you could pick up with one hand casts a shadow the length of a basketball court. Mountains, 75 miles away, throw shadows that reach all the way across the landing zone. Every dark patch you see is a question mark. It could be a 3-inch scuff in the regolith. It could be a 30-foot crater. There's no haze, no atmosphere, nothing your brain can use to judge depth. It just looks dark, and you won't know which one it is until you're already stepping into it. Apollo astronauts at the equator, where the sun was high overhead and shadows were short and honest, still routinely underestimated distances to landmarks by a factor of 2 or 3. They'd pick a boulder as a target, start walking toward it, and it would just keep not arriving. The near horizon and the lack of atmosphere threw off their spatial sense completely. At the South Pole, with the sun permanently glued to the horizon, that effect is dramatically worse in every direction. NASA studied this problem specifically for the South Pole mission, and their conclusion was blunt. Astronauts will be unable to avoid having the sun in their eyes for much of the time, and headlamps will be required constantly, even during what technically counts as daytime. You're on the moon, in full sunlight, and you still need a torch to see where you're walking. The horizon sits only 1.5 miles away, half the distance it is on Earth, so everything feels compressed and close, the landscape crowding in from all sides. And somewhere in all those long lying shadows is the edge of something you can't see the bottom of. Number 3, cold that can freeze your blood. The South Pole has craters that have never seen sunlight. Not in your lifetime. Not in the entire history of complex life on Earth. Some have been in complete unbroken darkness for over 2 billion years, since before the first fish had fins. Inside them, the temperature sits around negative 180 degrees Celsius. That's the warm ones. The coldest measured point on the moon, a crater near the North Pole, but representative of the deepest PSRs anywhere, hits negative 253 degrees Celsius, colder than the surface of Pluto, colder than almost anywhere else in the solar system. It is, as far as any instrument has ever recorded, the coldest naturally occurring location we've found anywhere. Not deep space, not the outer planets, the moon. And the crew is going to be working near places just like it. For scale, liquid nitrogen boils at negative 196 degrees Celsius. The floors of these craters are colder than that. Liquid oxygen, rocket propellant, stays perfectly stable down there. Your blood does not. The new Axiom-U spacesuit is rated for 2 hours inside a permanently shadowed region. 2 hours. After that, its thermal systems hit their limits. Apollo suits would have failed almost immediately in conditions like these, but it didn't matter, because Apollo never went anywhere near a PSR. The equatorial landing sites were warm, sunlit, and safe. The South Pole is none of those things. The crew has to approach these regions specifically. The cold is the whole point. It's why the water ice might be preserved down there. They're walking toward the coldest place in the solar system on a 2-hour clock in a suit that has never been worn in actual lunar conditions. Number 4, the rocket that needs 8 to 16 other rockets. Before the crew faces anything on the moon, before they even leave Earth orbit, their mission depends on something that has never been successfully done with human lives depending on it. Starship can't reach the moon on a single launch. The vehicle is too heavy when fueled, so it launches nearly empty and then gets refueled in low Earth orbit. That fuel comes from a depot. The depot gets filled by a series of dedicated tanker rockets, somewhere between 8 and 16 launches, depending on which estimate you trust. SpaceX says 8. NASA has cited up to 16. All of those launches have to happen in roughly 3 to 4 weeks, not because of scheduling, because of physics. The propellants are cryogenic liquid methane and liquid oxygen, and they're constantly boiling off into space. Every day that passes, propellant disappears. Too many delays between tanker flights and the fuel is gone, the depot empties, and the whole campaign scrubs. The technique that makes this work, transferring cryogenic propellant between 2 spacecraft in orbit, has never been demonstrated. Ever. The first test is planned for sometime in 2026. The crewed landing is targeting 2028. There are 2 years between first test and human lives depend on it. Apollo launched on 1 rocket. Neil Armstrong sat on top of one Saturn V, lit the engines, and left. He did not wait for 15 other rockets to complete an unproven refueling chain before he was allowed to go. The next crew boards their spacecraft knowing that the question of whether they can even reach the moon was only answered a couple of years earlier, under test conditions, with no one's life in the balance. The first time it happens for real is the mission. Number 5. Moonquakes that don't stop. When an earthquake hits, it lasts seconds. A major one might drag on for a minute or two. Then, the energy dissipates through water-saturated rock and soft sediment, and it's over. That's just how a geologically active, water-soaked planet works. The moon doesn't work that way. The moon is dry and rigid all the way through. When it shakes, there's nothing to absorb the energy, so it just rings, like a bell struck with a hammer. Shallow moonquakes can sustain for over 10 minutes continuously. Deep moonquakes can keep the surface trembling for hours. Apollo seismometers, left running on the surface from 1969 to 1977, recorded 28 shallow quakes before NASA shut them off. Some hit magnitude 5.5 on the Richter scale. That's not a rumble. That's a building shaker. Nobody was standing on the surface when any of them happened. Here's what makes this specific to the South Pole. There's a fault system in the landing region called the Lee-Lincoln Scarp, a long, fresh crack in the lunar crust where the surface has buckled as the moon contracts. The moon is still cooling, still shrinking, and as it shrinks, the crust cracks, and those cracks cluster near the South Pole. In 2023, researchers fed the old Apollo seismic data into an AI model and found moonquakes near the pole that nobody had identified at the time. The signals were there for 50 years. We just couldn't see them. The fault is active. The quakes are real. And the vehicle sitting in the landing zone is a 50-meter rocket with a very high center of gravity on sloped terrain. A multi-minute magnitude 5 event could tip it. Not hypothetically, engineers have flagged this as a real structural concern. Apollo's lander was 7 meters tall on flat ground, and still nobody wanted to be standing next to it during a moonquake. The next crew doesn't get flat ground. Number 6, dust that fights back. Every single person who has ever walked on the moon came back sneezing. Red eyes, scratchy throat, nasal congestion. The dust got into the cabin on their suits every time they cycled the airlock, and there was no way to keep it out. Harrison Schmitt, the geologist on Apollo 17 and the last scientist to walk on the moon, had it the worst. His voice audibly changed on the recordings as the mission went on. Lunar dust is not like any dust you've encountered. On Earth, particles get tumbled by wind and water for millions of years until every sharp edge wears smooth. Lunar dust has never been weathered. It's been shattered by 4 billion years of micrometeorite impacts, and every grain is jagged and angular and chemically reactive in a way terrestrial dust simply isn't. It's more than 50% silica. On Earth, long-term exposure to fine silica causes silicosis, irreversible lung scarring. Nobody has ever kept a human on the moon long enough to find out what it does up there. But the physical damage is only part of it. The dust is electrostatically charged, UV light from the sun builds up charge on the surface, and during intense solar activity that charge reaches negative 5,000 volts. Grains lift off the ground by themselves with nothing touching them, jumping centimeters into the air under their own electrical repulsion. Apollo astronauts reported a strange glow on the horizon at lunar sunrise. NASA later determined it was electrostatically lofted dust rising in clouds several kilometers above the surface. At the South Pole, the terminator, the boundary between sunlit ground and permanent shadow, sits right on top of the landing zone. That's where charged and uncharged dust meet, and nobody has ever been physically present at that boundary to measure what actually happens. The models make predictions, the physics suggests it gets strange, but the data doesn't exist yet because no one has stood there. Within 3 days, Apollo 17 suits had 3 Kevlar-like layers worn through on Jack Schmitt's boots. The next mission is planning 7 days. The new AXIMU suits have anti-dust coatings developed specifically for this. They have been tested in laboratory chambers filled with simulated lunar regolith. The moon has not read the lab results. Number 7. Comms blackouts with no one watching. Apollo astronauts were always on the near side of the moon, on flat equatorial plains, in full sunlight. Earth was always visible above them. Houston was always one radio bounce away, and if something went wrong, mission control knew about it within seconds. The South Pole breaks that completely. The moment the next crew descends into a crater, and they have to, because that's where the ice might be, they drop below the rim and lose direct line of sight to Earth. No signal to mission control. No signal to the gateway station in lunar orbit. No way to call for help. If something goes wrong at the crater floor, Earth doesn't know until the crew climbs back out and tells them. We have a real preview of what this silence feels like. During Artemis II in April 2026, the Orion capsule lost all communication with Earth for roughly 40 minutes during its far side flyby. That was in orbit, nothing going wrong, the crew sitting safely inside the vehicle. 40 minutes of total radio silence. The crew knew it was coming, knew it would end, and still had to just sit there with the quiet. There's a fix being built, a relay satellite constellation that will keep the South Pole in continuous contact with Earth, routing signals around the geometry. The first satellite is targeting 2027. The full network is expected sometime in the early 2030s. The crewed landing is targeting 2028. The math is uncomfortable. During the most dangerous moments of the mission, crater descent, PSR approach, sample collection at the edge of permanent shadow, the crew may be operating in scheduled communication blackouts. Not emergencies. Scheduled. Windows where Earth cannot see what's happening and cannot respond if something goes wrong. The plan accounts for them. That's almost more unsettling than if they'd missed them entirely. Apollo had a lot of problems. Flying blind into a crater with no comms wasn't one of them. Number 8, an Earth that won't move. This is where the video changes. Everything up to here has been about things that can kill you. The elevator, the cold, the quakes, the dust, the silence. Those are engineering problems. Terrifying ones, but the kind of terrifying that has a checkbox somewhere, a test result, a certification, a backup someone is actively designing. hard problems with the shape of solutions. This one doesn't have a checkbox. When Buzz Aldrin stepped onto the moon in 1969 and looked out across the surface, he called it magnificent desolation. Earth was in his sky, blue and whole and moving, rising, tracking slowly across the stars, a familiar thing doing familiar things even from 250,000 miles away. The universe felt like it was still going somewhere. It felt traversable. At the South Pole, Earth doesn't move. It sits in the same fixed patch of sky for the entire mission. Low on the horizon, not high and proud like you'd imagine, just low. And it appears rotated wrong backwards from how you see it at home, phases running opposite to what you'd expect. And it stays there, wobbling a few degrees over the course of a month. Watching. For 7 days straight, it is in exactly the same spot every time you look up. There's no sunrise, no sunset. The sun slides along the horizon but never actually crosses it, so there's no morning, no evening, no moment where the light shifts, and your body gets the signal that a day has passed. The shadows are the same length when you wake up as when you went to sleep. Time stops feeling like something moving and starts feeling like a place you're trapped inside. Research from the International Space Station and from scientists who winter over in Antarctica, months without sunlight, no natural day-night rhythm, shows that circadian disruption of this kind is psychologically corrosive in ways that build slowly, not a dramatic breakdown. Just a quiet, cumulative erosion of the thing that makes you feel like yourself. Buzz Aldrin came home from 21 hours on the surface and spent years putting himself back together. Depression, alcoholism, he talked about it publicly, which almost nobody did at the time. He said part of it was the weight of having done the greatest thing a human being had ever done and having nowhere left to go. Part of it was something harder to name. Something about having been there. The next crew is staying for a week. Every time the airlock cycles, the cabin fills briefly with the smell of gunpowder. That's what lunar dust smells like when it hits cabin air. Every astronaut who's ever been to the moon agrees on this. And then it fades, and the only sounds are the hum of the suit fans and the sound of your own breathing. The suit fans are important. If one of them stops, you hear the silence before any warning light comes on, and Earth just hangs there, low, wrong, still. Number 9. The water might not be there. Here's the thing nobody is saying loudly enough. The entire reason the next crew is accepting every single risk on this list, instead of landing somewhere flat and safe and sunlit like Apollo did, is water. Permanently shadowed craters at the South Pole are supposed to have water, ice locked inside them, preserved in the cold for billions of years. The plan is to extract it and drink it, and to split it into hydrogen and oxygen and burn it as rocket fuel. That's called in situ resource utilization, and it's the foundation of the whole argument for going to the pole in the first place. Without it, the South Pole is just an extremely dangerous place to land with no particular advantage over anywhere else. In 2009, NASA deliberately crashed a rocket stage into a south polar crater and analyzed the debris cloud. They found water ice, about 5.6% by mass. Promising. Enough to build a strategy around. Then, in 2025, new data arrived that didn't make nearly enough headlines. An instrument called ShadowCam, riding aboard a Korean lunar orbiter, imaged the permanently shadowed regions in detail that no previous mission had managed. It found no evidence of pure surface ice deposits. Most craters came in at less than 5% water by weight, some registered essentially zero. Separately, a radar study conducted from Earth put hard upper limits on the ice content that were significantly below the optimistic earlier figures. Everything above this point is established measurement, real data from real instruments. What follows is the implication, and it's worth being honest, that it's an implication. If the crew gets there and the ice is sparse or inaccessible, the strategic argument for accepting every item on this list gets very hard to defend. The honest scientific answer right now is that we don't know how much ice is actually there. We don't know until someone drills. And drilling is what this mission is for. They're going to the most hostile, most technically demanding landing site in the history of human spaceflight to find out if the reason for going is real. They are risking everything to dig for water that might barely exist. Number 10. A week of magnificent desolation and what it does to a person. The longest any human being has ever spent on the surface of the moon is 3 days. Apollo 17, December 1972. Gene Cernan and Harrison Schmitt. That record has stood for over 50 years, and in that time, no one has come close to breaking it. The next crew is planning 7 days. Not 3 days with better equipment. 7 days. More than twice the longest anyone has ever done, in a stranger environment with longer blackout windows, with a fault line active underneath the lander, with dust eating through the suits on a clock that Apollo already proved was shorter than 3 days, with no natural day-night cycle, no sense of time passing, and Earth locked to one spot on the horizon like it's been nailed there. No human mind has ever held this particular combination of things for a week. There is no analog study, no simulation, no ISS equivalent that replicates all of it at once. We genuinely do not know what it does. What we do know is what 3 days did to some of the toughest, most accomplished, most psychologically screened human beings ever selected for anything. Buzz Aldrin came home from 21 hours on the surface and needed years to find solid ground again. He was honest about it in public at a time when that kind of honesty cost something. He said he had done the greatest thing a human being had ever done, and then he had to come home and be a regular person, and those two things did not fit together. He said the moon itself was part of it, the weight of having actually been there. The next crew will stand on the moon and smell gunpowder every time the airlock opens. They will hear only their own breathing and the fans keeping them alive. They will watch Earth hang motionless on the horizon, not rising, not setting, just present, low and wrong and watching, for 7 straight days. And at the end of it, if everything goes right, they will ride an elevator back up to their spacecraft, leave the moon behind, and come home to a world that will never quite look the same again. Buzz Aldrin looked up and called it magnificent desolation. But Earth was moving across his sky. The next crew gets Earth standing still, staring back at them for 7 days straight. The question isn't whether they can survive the moon. It's whether they can survive coming home from it